Hi, everybody. Good to have you here attending this new webinar. As most of you at least may know, this webinar series is held every Wednesday. So we will have this appointment, let's say, every week up to December 16, okay? For those of you or your friends who cannot attend the webinars during the direct phase of the presentation of the lecture, it will be possible to see them afterward, because we will have the recorded version of the webinar on our YouTube channel. The exact address will be published in a few minutes on the right side of your screen, where you can see the link to attend or just to see the lecture again. Today we have a lecture by a young surgeon and a friend. Is Łukasz Juszkiewicz from Poland, and Łukasz graduated in 2005 in Warsaw University, Warsaw School of Medicine, veterinary medicine, and he is now running his own clinic in Puławy, and he is also an orthopedic consultant for other clinics in Poland and abroad, especially Sweden as well. He's a relatively young surgeon, but is very enthusiastic one, and he has this kind of approach that I like the most, meaning that is thinking how to develop, how to improve, how to make something new and better than in the past. As you may know, at the end of the lecture, about 1 hour, we will have question session. You can write your questions on the chat that is on the right side of your screen. So you can write down your question, and Łukasz eventually will answer to your questions. We will have 2 advertisement breaks during the lecture, but I can guarantee you it's just a couple of minutes each, so nothing really bad. And of course, TV has its own requests and demands. Okay, so thank you very much. If you want to see the complete list of the webinars, you can go to our website. There is the updated list of the webinar, just to check for speakers and topics. Okay, see you later. Thank you. Łukasz, please switch your mic on.
All right. All right.
Okay, good.
Okay.
Check your sets, please, so that, okay, good.
All right. Okay, so starting from the beginning. So my name is Łukasz Juszkiewicz. So for the non-Slovian participants, it's maybe easier to say just Łukasz. And at the beginning, I'd like to say big thanks to Gianluca and the whole Maiora team for inviting me and organizing this meeting. I'm a veterinary surgeon. I do some surgeries in Poland and in a few clinics in Sweden. Sometimes I do consults in Dubai, where I used to work for some time. Today topic is it's a 3D printing, and I think we can move on with a presentation. Okay, so 3D printing is it's a very popular subject in the last few years, and it's getting more popular within last few years, and now it's a future of our medicine. So it's a process that we can have a three-dimensional solid objects of any shape, and we can print them from digital model. And that's the theory, and it's right now 3D printing is used in different sectors, in industry, in medical, pharmaceutical, food, fashion, households, all others. To make everybody more interested, there's those two pictures here, and this is a model of angioma tumor in human, and 3D printing gives us that possibility that we can paint our tumor in green, and all the surrounding vessels can be in red. On the right side, it's a topography of veins and arteries of a little heart, and the pathological ones are marked with separate colors, so the cardiosurgeon can plan the surgery just before the days before the operation. All over the world, it's used. 3D printing is used widely, and the biggest example and the biggest 3D printing object so far is the whole building that was printed in Dubai, and you can see here this big and black yellow thing. It's a massive FDM printer, and this printing was organized by Dubai municipality, and it was a dream of Sheikh Mohammed Al Maktoum that he wants 20% of buildings to be built via 3D printing in next few years. Okay, let's get back on Earth. We have different technologies in 3D printing, and the most commonly used and those that we use in our practice. The first one that we need to talk about is FDM. FDM stands for fused deposition modeling, and this is the one that we see when we want to go to the shop and buy a printer. That's what we get. We get FDM. So we get the machine that prints from the melted filament, and it just lays the filament in layers, and when it dries, we get our object. And this method allows us to print in ABS, so classic plastic, polylactic acid, and nylon. And those two, we will have examples today. Bioprinting, that's something that is really interesting, but we will not talk about it today. But the bioprinting gives us a chance to use the biomaterials in a nozzle of a printer. And so we can print the objects straight away that we can implant into the body. We can even have an option of two nozzles, that one prints a scaffold, another one prints a gel that fills it up. And third method that we will be talking about today, it's SLS, and it's also used for harder objects, where we have also layers of material, but the material is powdered, and the laser melts it together in a specific pattern to form our object. Very similar method, it's EBM, and it stands for electron beam manufacturing, this one, and it's more or less the same, just instead the laser, we have a high power electron beam that is used for melting our particles, and that is used for titanium. So that's most probably how John Lucas TTA porous implants are made. And example of that is this really nice hip replacement implant together with a dorsal acetabular rim. All other methods are also use, but not so much in veterinary medicine right now. Maybe SLA a little bit, because we can use we can print polypropylene from those with this method. Okay, so what we need to do to get the final printout? Okay, we have to collect the image, and it can be designed by an engineer in a CAD software like CAD, or we can get it from a CT scan, from MRI scan. We can even collect it through 3D scanners. Right now, 3D scanners are getting more and more handy, more and more portable. There's even software that you can use your mobile phone to get a proper three-dimensional picture of an object. And then we transform it to a DICOM file. So DICOM file, it's a medical format for our files. And the next step is transforming DICOM file to the format of STL, and STL stands for stereolithography. And this is the most commonly used format for 3D printing, and this is the file that the printing software understands it. So at the level of a printing software, we have to work on the surface of our implant, on a mesh correction. We have to set the proper layers that are specific for the printer. Then we choose a proper printer, proper material we want to use, and after a few hours we can have our printout. Pretty often we have to also do something with this print after when we have an object on the table. So because we can use our 3D printed object as a scaffolds, or we can cover those objects with hydroxyapatite, with a calcium, or we have to work on the surfacing of those implants. All right, so that was the theory. Let's have the fun part. As you see on the picture, that kid was born with a malformed hand, and the scientists decided just to give him a proper hand prosthesis, but they also printed him this fancy Thor hammer. So as you see, 3D printing can be fun, and it also can do a lot of good things. All right, going back to this case, this is one of my favorite ones, because here we had to print the model to plan the surgery, we had to print the guide to help us with the surgery, and we had to print a proper implant that solve our problems at that moment. And our first patient is BAMSE, and my first thought about BAMSE, it was I got back to that quote of Mr. Gramsci. That's not BAMSE, that's Mr. Gramsci. So if you beat your head against the wall, most probably it's not the head that will break. It's your head that will break, not the wall. And why? That's the BAMSE, and BAMSE is a very active young hunting dog that went to a forest for a quick run and got back with a massive wound on his forehead. It's a special breed that lives there. He lives in Arvidsjaur, just below the Arctic Cycle, and from the young days they are taught to chase elks and to help people to hunt them. And BAMSE got back from his walk with this kind of injury. He was wagging his tail. He was pretty happy, but the hole was pretty serious. So the local surgeon removed the loose pieces of bone, and the one piece she put back on a place here, and then she stitched everything together, and then she sent me an email. Okay, Lucas, what to do? So we decided to do a CT scan just to know how we can help him, and that's what we received. We received a pretty big gash in his head. We received flap from the loose bone that was placed on its original place, but not really. Okay, it was proper, but was not very accurate. And then we have visualization of this, and we had few problems here to solve. So we had to think what to do with this gash here, with this gap. Is this going to be a problem or not? We decided that most probably it's not going to be a problem, especially that the time frame was pretty big from the injury to the scan and to the final surgery. Because of the distance, because the dog was in RVC, or scan was done in a city place that was a few hundred kilometers from their home. Then it had to be sent to Puławy, where we worked on our pictures, and then we decided what kind of print we had to do. And then we had to travel. I had to travel to Lapland, and then there was a time of surgery. So this is our implant. That was the shape that corresponds with the shape of the hole, and the problem was how to fit it on a place, because just the press fit was not good enough because the time that was passing, edges were not clear. So we decided to do a special guide, and as you see, guide has those flaps, and those flaps have holes, and there are two kinds of holes. One kind is for the pre-drilling for the screw placements, and the other hole is for the K-wires. We needed K-wires just to hold the guide on a place, because guide was used also to work on the edges of the lesion, so we can fit our implant properly. And that's how we went into a surgery room with BAMSE 3D printed skull, with 3 sets of implants and with 2 sets of guides, just in case if somebody drops it on the floor, and then we have a few hundred kilometers to print it again. So we wanted to be double sure that it's all fine. Okay, and surgery time. Surgery time, as you see, we use a normal classic Artrex shaver to work on the edges of the wound, and after that we placed implant on the site, and we stabilized that with a 2.7 millimeter locking screws. Why locking screws? Locking screws because we decided that the thread on the head of the screw will lock itself into the nylon of that flap, and it worked well. And right from this perspective right now, we think it was a good decision. There was no problem with we checked the flap, the higher flap there. It was totally not movable. It fused nicely, so we decided not to touch it. Even that the highest screw here, the most caudal screw, is placed through this flap, and it didn't move at all. Okay, so this is our X-ray, and okay, it's a hedgehog-style dog. So those screws are not really interfering with anything. They hold in place. And BAMSE, okay, he's got a funny hairstyle, but he recovered super quickly from the surgery. He went home, and owners got back to his normal activities, to his normal training. And I was really surprised to receive an email after 3 weeks, and that's BAMSE 3 weeks after the surgery with his first elk, that he did his job and showed that elk to the hunter. Okay, we may not agree with hunting, but that's what those dogs live for. They're born for that, and they love that. Okay, so maybe it's time for a Maiora spot right now. Okay. All right. Now there's a second case, and it's a slightly different situation. Not everything here is printed, but implant is printed basing on a CT scan, and it's a dog with a big dog with a big problem. Dog was called ARAMIS. He was a 6-month-old Great Dane, and suddenly had acute lameness on his left leg, and the local surgeon found a pretty massive tumor on his proximal radius, and they contacted us to help them to do something with that. Owners were quite experienced breeders. They decided that they don't want to go for amputation, and local surgeon did biopsy, and the histopathology of that lesion told us it was osteoma. Okay, and this is those are pictures from that CT scan. You can see here in this area, that's a place after biopsy, somewhere here. See, it's pretty big ditch that was done here. So there's a big chunk of material that was sent there. So we were pretty happy with that result, because we were told it was benign, and we couldn't find any problems with the ulna and with the distal humerus. Condyles were intact. They were fine on the place. So the plan was to work on something that we can remove the tumor, and we can replace it with some sort of implant that will give this dog stability and give this dog proper mobility then. As you see, the whole depth of the bone was damaged, so there was no chance to save it. Opposite part, we did a scan of 2 legs, because we were hoping that we can use the scan of the opposite leg to prepare the implant basing on that opposite leg, just on the mirror picture, on the mirror image. But to achieve that, we had to explain everything to the owners, and just the very basic printouts made of like a poor quality nylon helped us to do that. So we explained, okay, can you see a difference between right and left? And our plan is just to how to print the bone like this and just put it here. So it really helped with a communication with the patient about pretty complex surgery. We had few problems with this case, because there's not so many cases in the literature about lesions that long. We had a technical problem. Our first thought was titanium as a material, but first it was super expensive, and then there was a technical problem to print that long titanium implant. Another question was, okay, should we do arthrodesis? We thought, okay, yes, we have to do arthrodesis, because removing the tumor, we had to destroy all of the soft tissue around the joint, and so the stability of the joint was very, very poor. Owners decided that they didn't want to go for a chemo. So we told them, okay, because of the weight of a dog, because of the on one side we had the weight of the dog, we had the lesion that is pretty big, but on the other side, okay, we have a young dog, and we were told that the lesion is benign. So our prognosis was just guarded. Our choice was a nylon, and not titanium, because nylon is cheaper. We could cut it. As you see, this implant was printed much longer than the one that we actually needed there. you can drill it, you can put the plate on it, and you can sterilize it in an autoclave, which is important because in many biomaterials, we're having really big problems with sterilizing them. Okay, titanium not, but all the biomaterials that we use for scaffolds, they start degrading in 60 degrees. So we have to find different ways to sterilize them. Okay, so my wife asked me why it's black. I had to answer that it was because it was a black dog. So okay, so nylon as a biomaterial is known for long time. We use it in the normal classic surgery almost every day using nylon sutures. Most commonly on the skin, but also for ruptured tendons. Nylon has this kind of specific features that they make it really perfect for building scaffolds than to build some other tissues on those scaffolds. But in this case, we didn't need a proper scaffold. We just needed a big chunk of nylon that will transmit forces that they go from the elbow down on the distal radius. Okay, so this is a ARAMIS after the surgery. So this is one of those cases when owner is paying for something that he cannot see. So it's some sort of fate, I think. Okay, so believe me, there is an implant inside there, and it's connected with distal radius with locking plate. It's a polyaxial plate, so we could those screws on the edge, we could put them with different angles just to get little bit more bond purchase. Here is a lug screw connected to from the upper part to the lower part, connecting our implant with the ulna. And here we have a Ostilock big plate that gave us really nice stability for that arthrodesis. That you can see quite a lot of implants here, and this is a screw holding osteotomized olecranon, and that is unfortunately broken drill bit. That happens sometimes, but it was subclinical, and that's how it looked after the surgery. I was a little bit scared about this long arm of the plate here that will bring too much friction on the joint, but nothing like that happened. Dog walked really well on that for a quite long time. Here you can see a shape of the implant actually. Okay. And that's all three pieces of puzzle for ARAMIS. Okay, I'll just switch on the light. It's getting dark. And that's our final printout that we final model. And this is the one that we sterilized as well. We took it with us to the surgery room. So if we were a little bit blinded with our approach, with the surrounding tissue, with those additional artificial vessels going to the tumor, we had that to look at. This is the growth that was removed, and it was like 2-3 centimeters from the tumor itself that was cut off. So we thought, okay, that is pretty safe. Unfortunately, this proximal part was really damaged. There was not much left from the bone there, and that's our implant. As you see, it's a little bit longer, so we decided to cut it there, and it fitted very well into the space after this tumor, after this change proximal radius. We were not so worried about fitment, first because we had the second one, and third that we had to unfortunately do the arthrodesis of this elbow. And this is ARAMIS post-op, and he was doing super well for 6 months. Unfortunately, after those 6 months, there was a regrowth of the tumor. Okay, we were not so happy about this result, but owners had time to say goodbye. Dog had a painless life for 6 months. As the owners were totally against the amputation of that limb. So, okay, we can discuss if it's ethical or not ethical, if it's right or not. I think it was the right thing to do because we gave this dog quite long time of functioning in a good life quality. Okay, so the third situation that I'd like to talk about today is it's a situation where we use different kind of implants. The implants are 3D printed, but for the material that we can use it as a scaffold. So scaffold means that we can cover this material with cells that that are handy for us, or we can cover it with substances that they promote some kind of growth. And this case here is case of ZITA. ZITA was 8-year-old Amstaff with jaw tumor based on the premolar area. It was hanging out from the mouth a little bit, but was ingrowing into the bone. Owners noticed that fairly early, and then surgery was done pretty quickly, so we were happy that okay, everything will go nicely. First symptoms was a bad smell from the mouth, painful chewing, enlarged lymph nodes. But on the other side, we had a good blood result. There was good CBC, good biochemical. ZITA had a good biochemical parameters, and she was in a good shape. Because of the character of jaw implants or jaw tumors, I'm sorry, we told owners, okay, there is a high chance that it can be malignant. But owners decided, okay, even that, we are not ready to say goodbye to her. Let's try. So that's why I wrote here that it was a palliative surgery. And we decided to go for an implant made of a polylactic acid. And it was a cylinder shaped to a shape of a bone. And it was additionally covered with a HYDROXIAPATITE to stimulate transformation of the scaffold into a proper bone. Why polylactic acid? That's another material that is widely known in the medicine. It has FDA approval from 70s, from last century, and it's used in most obvious ones in tissue engineering, so scaffolds, but also patches for a urinary bladder, for the cartilage, for little holes in the in horses, for holes in the joints, for OCDs. It can be used as a delivery system for medications, for some particles that we want to put into the organs or into the specific areas. But also, polylactic acid is used as a suture as well. So again, we're using it for quite a long time, so we know how the body responds to this material. That's why we thought it's pretty safe. And in this case, we didn't have to use it, because nylon in ARAMIS case had to be really strong because of the forces distribution in that joint. Here we could use pretty solid plate on the side of the jaw. So implant itself, we were more focused about the abilities of that implant to form a bone after that. The total transformation of a polylactic acid to a bone, in theory, in vitro studies, is around 2 years. Okay, and this is the removed fragment. We tried to remove it as far as it was possible. Okay, we were not happy in time of the surgery with the margins, but histopathology told us that okay, it was removed within a healthy regions with a healthy tissue, and the result was malignant amautoblastoma. which is not that good. This is the implants that we used. So those are like a standardized cylinders with a different diameter that I just take to my bag and I go to Lapland to do some surgeries. And we used it for ZITA because we had a chance to drill in it. As you see, there is a screw in the implant, and it's pretty good solution. So we don't need any special arms, ears to hold it on a place. And on the right side, you can see those lines. Those are those lines. Those are those lines that they told us, okay, here is the implant. But let's see what's happening here. We have a bone formation here. So we have a densening of the implant, and that was doing really, really well. So that's ZITA 3 months after surgery. No symptoms, nothing. No bad breath. She got back to chewing her favorite toys. Again, there's an implant that you cannot see. You have to believe that it's there. And ZITA got 9 months survival time after the surgery. Owner was very happy. ZITA got 9 months of a good quality life, and the cake is a proof that owners agreed with our decision about this case. Another implant that I'd like to talk about. We use it in case of Post. Post was an active hunting dog, elk hunting dog, a little bit like BAMSE, but he was at the end of his career. And at the hunting session, he chased the elk. Hunter shot the elk, and the bullet went through the elk, and after ricocheting from the scapula, hit the dog while he was barking with an open mouth, and made a hole in the hard palate, and then went into the soft tissue around his neck. And the bullet was removed by a local surgeon. Wound healed up. Wound on the neck healed up nicely, but wound on in the hard palate didn't want to heal at all, and even despite using antibiotics and all kind of treatments, we were thinking that it's okay. It's a food mixing, but also it's the allograft of the elk tissue that was placed in that first entry wound. Fistula on the X-ray had a 5 millimeter diameter, so we decided to use this kind of implant that originally was designed for human medicine for trepanations. So after human skull trepanation, the hole was covered with a plug like this that is dipped in the blood just to deliver cells that we need for tissue regeneration, and it was just plugged inside, and the skin was closed without any suturing, without any plating. And in Post case, we use a little bit longer implants because fistula was longer, and the solution was pretty simple. We use a 6 millimeter drill to remove all the tissue. We sucked it out, we flushed it, and then we placed the plug into the fistula. We covered it with freshly collected blood, and as you see, this is this moment when we are putting it back on a place. Here is a gingival flap that we moved up. We put it back. We put the flap back, and then it was a matter of 2 stitches, and the surgery was done. That's the original wound. That's another ricochet that the bullet went on that tooth and went into the hard palate. And Post got back to his normal activities. He started going back to the forest. Unfortunately, he had to finish his hunting career because he was scared of shooting. But there was nothing with the implant. He still lives there. All right, we can have a place for a second at Maiora spot. All right, so this case is case where we had a pretty complex problem, and we use 3D printing model to plan the surgery, and also to be able to talk to the customers to explain them what we actually want to do with the dog. And it's a way that lots of orthopedic surgeons go right now. It makes our life much easier. It makes the surgery time much quicker, because we don't have any more situation that we open a cat, and we say, okay, what the heck now? What to do? And because we can have everything planned on the print that is printed in 1:1 scale, so we can contour the plates, we can plan the osteotomies, we can actually plan the approach to the bone, we can plan all angles, we can make mistakes, and it doesn't hurt anybody. We just need to print another model. Okay, and our patient here is Topaz. It's a 1.5-year-old German Shepherd, and he had a problem, three-dimensional right leg deformity, and he went through a ulnar osteotomy when he was in his stage of quick growth of his bones, and that went well, but in a way it was not good enough, because he was a quickly growing dog that time, and the osteotomy was prematurely closed. As you see, this is a scar after the first surgery. You can see a limb shortening. You can see the angles of the main issue was angle of the wrist, where we had a rotation, and it was a pretty bad valgus there. Okay, let's try to see if that will work. That's how he's running. He was running. Okay, again. As you see, leg doesn't look very straight. And the first thing that the owners said was like, hey, every neighbor tells us, okay, what's happening with this? What a nice dog, but what's happening with this leg? Those are the X-rays that I received, and as you see, the plane of the elbow and the plane of the wrist is totally off. You can see a little bit of procurvatus, little bit of valgus, or quite a lot of valgus, and you can see a big scarring of the of ulna. So we did a CT scan, and that's our printout. From the planning software, we agreed that we want to do osteotomy in this area here, and we mark those black lines to see our starting points. Then from the X-rays from our software, we decided how much we want to correct our torsion. So this is the length that actually told us about the angle that we wanted to rotate, because that line corresponds with this line here. And as you see, that's another use of TTA porous implants. As you see, they get handy in different occasions. And this is a TOPAZ just after the surgery. There's no more TTA implant here. We use the wedge made of the ulnar bone. Ulnar bone, we had to remove a little bit of that, and it was around 7 millimeters, just to make the rotation of our fragment possible. Well, the same markers that we put on our model, in the same exactly places, we place them on the bone. When we are happy about rotation, when we are happy about the look of our leg, we placed K-wires in a cross action, in a cross shape, and then we stabilize everything with Ostilock plate in the dorsal area, and then on the side of it, just to change an angle a little bit, that's locking 2.7 plate, and Ostilock was 3.5. And leg looks straight away more straight. The only issue was that we were not able to make this leg longer. That's because owners did not agree to go for a option with a circular fixator and lengthening of the bone. They couldn't afford that. And this is the X-ray 6 months after the surgery, and as you see, everything healed nicely. Unfortunately, one of the K-wires is left there. After rotation, it changed its angle, and we had to do too big damage to get it back. But it's not clinically important for us right now. And as you see here, the main rule of correcting deformities, so that the fingers have to head up to front, is accomplished. Of course, we had to look on the poly rules as well. And this is TOPAZ a few days ago, with a beautiful in a scenery of a beautiful Polish autumn, and that's the dog right now. As you see, he walks pretty well, and the neighbors, they say, "Hey, what a beautiful dog," and then full stop. We're really happy with the results, and we are in touch with the owners if something goes wrong with this implant. Okay, here we have a list of articles that I looked through preparing this little webinar, and from this point, I'd like to say big thanks to Maiora for inviting me, and also to the clinics that I cooperate for the trust they put in me, and to those two companies started by young guys in Poland. They literally can print everything from every possible material. If they don't know how to do it, or if they don't have a specific printer, they know a person who can do it. Okay, thank you so much.
Hi, Lucas. Thank you very much. I think it was a very nice lecture. And I think that is the kind of lecture that stimulates the way how surgeons can think about, they can do it, pushing a little bit the cutting edge of their skills. So we can have this kind of ideas that, of course, they perhaps won't be able to change dramatically the result, because this will stay in our hands. But it's, I think, an important step, a big step for let us know better understanding what we are doing. Okay, because when you look to what you showed, it was like looking, of course, to the exact anatomy of the patient to understand exactly what we had to deal with. And in my previous experience in the old years, the only way we had to appreciate what we are doing was just asking, it is straight? That was the only way that we had to appreciate it. So I think it was very interesting and very well explained. So I thank you very much for your input. And of course, if there is any question by the audience, we will, you will take them. Just waiting for 1 minute. In the meantime, I can just say that and say again that the link that you can see on your right on the chat column is the link where you can access our YouTube channel and have a look again to the recorded lecture that can be interesting simply because, as Aida Ramirez says, it's not only to remember everything, so just a quick review of the lecture can be helpful. Okay, I don't see any typing right now, so perhaps there are no. Okay, but nevertheless, okay, here.
Okay, I can answer only part of it because it was SLS, and it wasn't printed in our clinic. We use one of those companies that I showed you. Those are the guys that they are responsible for printing. I'm a surgeon. I just know a little bit about printing and the materials, and I really rely on them if they, we discuss every case, and this time we had to go for that. The same material was used for BAMSE for the flap on the head that I didn't mention on the presentation.
So what you mean is that you don't know exactly what kind of filament was used for printing.
Yeah, it was not even it was that SLS, not FDM. So I don't know exactly what type. It was medical grade nylon. That's for sure. We on that, and the problem we had with filaments when we printed that was that when it's very, if you have a structure that is like a cage, it's like your porous cage, you can drill it nicely. But if you have layers one by one, and then you're trying to drill it, then it splits the layers, and then you have two implants, not one.
Yeah, to have implants, perhaps.
Yeah.
Okay. Okay. Yeah, some typing, so we can expect new questions. Okay, thank you, Rosa, for your question. Rosa is an expert of this material because she works at the Complutense University, and they are working right now on this project for 3D printing in Madrid. So she is an expert in this in this field. Thank you, Sarab. Turkish colleague.
How often? It depends. It comes in waves. I would say. I think we do like 2 per month. Different ones. Not every surgery is that we use 3D printing as a guide, as a model, and as an implant. Very often we use just those cylinders, and that's good enough for us. When we don't have to, it's also about costs. So when we don't have to generate so much cost, we know what to do, and we just use the 3D printed implant for its purposes.
So do you mean that in some cases you will prepare the customized implants for the patient, and if you don't have budget enough, you may use also standard material that can be adapted in some way to the specific situation? Of course, not in every case this should be possible, but I guess like this, more or less.
Mm-hmm. Yes, exactly. So in some, like the most common use of 3D printing right now, it's for planning corrective osteotomies, and then the problems not always have to be sorted with a 3D printed implants. They can be sorted just with a standard implants.
Yeah. Yeah. Okay. Yeah. Yeah. Of course, the problem of costs in veterinary surgery is quite a big one, but
yeah, you know, right now when CT scans are more and more popular, and the resolution of those of that scanning, it's much better. Right now we have a 64 layer scanner, so that's pretty amazing. That's more than we need for printing right now, and that generates costs are much lower. Every half a year costs are much lower, so we see those scans more and more often, and then there is a gap for that 3D printing tool that we use as something additional, just to radiography or to
And this is a point that I like always to highlight to owners, related to the fact that sometimes to perform the best possible surgery is a way to spare some money, because if you don't make major mistakes, if you don't have to revise the surgery, if you don't need to make adjustments because the intra-op evaluation was mistaken by the fact that we didn't realize beforehand what we should do, this is in a way the best way for their investments. So of course, if they cannot afford for nothing, this is too low. Okay, nothing is always a bad number. But I would say that if we are able to maximize the result given the budget, this can be very helpful for planning and performing in the best possible way the procedure.
Okay. Sarab asked a question about the consulting clients, so patients. So if you guys would like to ask anything.
Okay, if you want, Lucas, you can type for specific questions. If you type your personal email address here in the chat column, those that potentially will need your suggestion can write to you personally. Okay.
Okay, yalla, go. Done.
Okay, so here you can see Lucas' email address, and this can be helpful for anybody who may need further comments or explanations or just suggestions, so that you can use this email address for personal requests. Okay, thank you very much, Lucas, for your availability, for giving your contact. Yeah, I think this is the good part of this kind of meetings, meaning that there is also the sharing of experiences and skills, and so this is fine. Okay, I think if we don't get any more questions, we can stop this webinar here today. Please remember the YouTube channel, and please register to the YouTube channel if you want. And remember that if you want to check for the calendar of Wednesday webinars, you can do it on our website, at Maiora website, so you can check for speakers and topics that we will deal with. Okay, thank you again very much for the beautiful lecture, Lucas, and as usual, keep in touch.
Right, thank you so much.